In this problem, we have a setup where an electrically charged sphere is hanging from a spring. It is also being acted upon and pulled downwards due to the electrostatic attraction between it and a negatively charged particle a short distance below it. Let's begin working through this problem by setting up a free body diagram showing the different forces acting on this positive sphere. Here is the sphere. Now acting upwards on the sphere is the force due to the spring, F sub s, which, according to Hooke's law, is equal to the spring constant, K, multiplied by the displacement of the spring, which is given in the diagram as this variable d. So F sub s is equal to kd. There is also a downward force acting on the positive sphere, because it is being pulled by the force of electrostatic attraction towards the negative charge. So this is the electric force, F sub E, or the Coulomb force. Now the problem describes the positive sphere as being small and gives us no information about the mass of the sphere, so it seems that we're meant to assume that the positive sphere is massless and therefore unaffected by gravity. So we're not going to represent gravity on our free body diagram. We're just going to assume that the net force acting on this particle is merely the sum of two forces: the force due to the spring, the upward force, and the opposing negative downward force from the electrostatic. Since the problem tells us that the sphere is at equilibrium at this point, that means the sphere is not moving, and the net force as a sum of these other forces is equal to 0. We can expand this formula out a bit too, because as mentioned earlier, the spring force is equal to kd, and the electrostatic force is the result of Coulomb's law, which states that the electrostatic force is equal to the Coulomb constant K, multiplied by the product of the magnitude of the charges of the two objects, divided by the square of the distance between them, which is r. And that is what is equal to 0. Now this problem is asking us to find the spring constant, which means our goal is to find the value of k. So we're going to use some pretty basic algebra to get k on its own. First off, we're going to add the Coulomb constant equation to both sides of the equation to find that kd is equal to k, and I really should add a subscript by the k to indicate that this is two different k's we're dealing with. So the k on its own is the spring constant, and k sub e is the Coulomb constant. So k sub e, the Coulomb constant, multiplied by the charges, divided by r squared. So we're now going to divide both sides of the equation by d to get k on its own. So k is equal to the Coulomb constant, multiplied by the product of the charges, divided by d, r squared. So all that's left for us to do in this problem to solve for k is to plug in our values into a calculator, based on the values that were given to us in the problem. So the Coulomb constant has a value of 8.99 times 10 to the power of 9 Newton meter squared per Coulomb squared, multiplied by the magnitudes of the charges. So the positive sphere has a charge of 0.8 nanocoulombs, or 0.8 times, actually that's microcoulombs, so it's times 10 to the power of negative 6 coulombs, multiplied by the magnitude of the charge on the negative particle, which is given as 0.6 microcoulombs. So again, times 10 to the power of negative 6 coulombs. We divide this by d, and d is given in the problem as 3.5 centimeters, so that's 3.5 times 10 to the power of negative 2 meters, multiplied by the square of r, which is given as 5 centimeters. So 5 times 10 to the power of negative 2 meters, and then we square that much. Put this into a calculator, and we find a value for the spring constant of 49.3 newtons per coulomb. or newtons per meter. And that is it for this problem. I hope this video helped you out. If it did, please consider subscribing, as it'll help me out in making more videos just like this. If you have a request or a question, leave a comment down below, and I'll do my best to help you out as best I can. That's all for now, and I hope you all have a lovely day. Bye-bye.